At 8:14 a.m. on August 6, 1945, Dr. Yoshio Nishina sat in his laboratory at the Riken Institute in Komagome, Tokyo. Nishina was Japan's preeminent nuclear physicist. He had studied under Niels Bohr in Copenhagen, intimately understanding atomic theory. His contributions to physics included the Klein-Nishina formula. For the past 3 years, since 1942, Nishina had been leading Japan's atomic bomb project, codenamed NIGO. That morning, he was working on the problem of uranium enrichment. Nishina had performed the calculations. To build an atomic bomb, approximately 50 kilograms of uranium-235 were required. However, uranium-235 constituted only 0.72% of natural uranium. The rest was non-fissile uranium-238. Separating these nearly identical isotopes demanded extraordinary technological sophistication. The thermal diffusion method his team developed was slow. Their prototype columns produced only minuscule amounts of slightly enriched material, a few grams. They needed kilograms. At their current rate, it would take decades. Nishina had repeatedly assured the Imperial Japanese Army that while an atomic bomb was theoretically possible, no nation could build one during wartime. The industrial infrastructure required was simply too massive. He calculated that the Americans would face the same impossible barriers. They might have more resources, but the fundamental laws of physics didn't care about industrial might. Uranium-235, Nishina firmly believed, wouldn't separate itself any faster in America than it did in Japan. He was tragically, catastrophically wrong. At that exact moment, high above Hiroshima at 31,000 feet, the B-29 superfortress, Enola Gay, piloted by Colonel Paul Tibbets, was on its final approach. In its bomb bay sat Little Boy, a gun-type fission device. Inside this weapon was 64 kilograms of highly enriched uranium-235, enriched to an astonishing 80% purity. This single quantity represented more processed uranium-235 than Nishina believed could possibly exist anywhere on Earth in 1945. The Americans had not merely solved the problem Nishina thought unsolvable, they had achieved it on an industrial scale that defied comprehension. While Nishina struggled with laboratory-scale equipment in Komagome across the Pacific, the United States had embarked on the Manhattan Project. In the remote hills of eastern Tennessee, a facility that didn't officially exist had bloomed into an industrial metropolis, Oak Ridge. By 1945, it housed nearly 75,000 residents, its existence masked by wartime secrecy. Within Oak Ridge, the Americans pursued multiple parallel paths to uranium enrichment. One path led to the colossal electromagnetic separation plant known as Y-12. This complex, covering 825 acres, housed 152 massive calutrons. These electromagnetic separators, named after the University of California cyclotron, operated on the principle of mass spectrometry on an industrial scale, using powerful magnetic fields to deflect uranium, separating U-235 from U-238. Each calutron required enormous electromagnets. Copper, the conventional choice, was critically scarce. In a testament to the project's seemingly limitless resources, the Americans borrowed 1,400 to 1,700 tons of silver bullion from the U.S. Treasury to wind the electromagnetic coils. Most of the 75,000 workers at Y-12 had no idea what they were building. The entire city had been conjured from rural farmland in just 2 years. Thousands of miles away, in the arid landscape of southeastern Washington state, another secret city had materialized: Hanford. This enormous site, employing over 50,000 workers, was dedicated not to uranium enrichment, but to the production of plutonium. Here, massive nuclear reactors, The B, D, and F reactors transmuted uranium-238 into fissile plutonium-239 through neutron bombardment. The plutonium, chemically distinct from uranium, could then be separated. The Americans had pursued multiple paths simultaneously for both uranium enrichment, gaseous diffusion at K25, electromagnetic separation at Y22, and thermal diffusion at S50, all at Oak Ridge, and for the creation of alternative fissile materials, plutonium production at Hanford. This audacious strategy of hedging their bets with overwhelming industrial efficiency was entirely alien to the Japanese program, which was struggling to make a single method work at laboratory scale. Nishina, secluded in his war-ravaged laboratory, knew none of this. Neither did any other Japanese scientist. They had convinced themselves that American industrial might, while formidable in conventional warfare, would prove irrelevant against the immutable laws of nuclear physics. The physics, they believed, was too difficult, too fundamentally challenging, for even America's vast resources to overcome in wartime. At 8:15 a.m. and 17 seconds, Hiroshima time, Little Boy detonated 1,068 feet, 600 meters, above the Shima Surgical Clinic in the heart of Hiroshima. The air temperature at the epicenter instantly reached 18 million degrees Fahrenheit, 10 million degrees Celsius, in less than 1/1,000,000th of a second, hotter than the surface of the sun. The blast wave propagated outwards at an initial speed of 984 miles per hour, 1,084 km/h, obliterating everything in its path. In that horrific first second, an estimated 70,000 to 80,000 people died instantly. Within minutes, the mushroom cloud began its ascent, eventually reaching over 40,000 feet, 12,000 meters. In Tokyo, Dr. Nishina knew nothing yet. Communication systems across Japan were primitive and severely degraded by August 1945. His Riken laboratory had survived, but information traveled slowly, hampered by damaged telegraph lines and overwhelmed military channels. The first reports were chaotic. At 8:16 a.m., Hiroshima's NHK radio station inexplicably went dead mid-broadcast. Military communications from the city simply ceased. Initial reports suggested a massive conventional bombing raid, but something was strange. There had only been 3 aircraft involved, the Enola Gay and 2 accompanying observation planes. Typical B-29 raids involved hundreds of bombers. 3 planes couldn't carry enough conventional ordnance to obliterate an entire city. By noon, more fragmentary reports, increasingly horrific, began to reach Tokyo. Survivors described a single, colossal explosion, a blinding flash, brighter than 1,000 suns, a giant, column-like cloud rising into the stratosphere. Eyewitnesses recounted buildings of reinforced concrete simply having been vaporized at ground zero. People had been reduced to grotesque shadows burned into stone walls and pavements. Nishina heard these chilling reports with growing dread and horror. He, unlike most of his compatriots, understood immediately what others did not. The horrifying descriptions, the sheer scale of the instantaneous destruction, the searing thermal effects, all matched the theoretical predictions for an atomic explosion. Yet, his mind resisted the conclusion. It was impossible, he must have muttered. The Americans couldn't have built such a bomb. My calculations proved it. By 2 p.m., the Imperial Japanese Army, deeply alarmed, dispatched investigation teams. These teams included several of Nishina's colleagues from the Riken Institute, notably Dr. Sakai Shimizu and Dr. Itaru Imai, carrying rudimentary Geiger counters and radiation detection equipment. If this had been an atomic bomb, the lingering radiation signatures would be unmistakable. Meanwhile, at the heavily damaged Imperial Palace, Emperor Hirohito was receiving the same fragmentary reports from his bewildered high command. The Supreme Council for the Direction of the War, the Big Six, was confused. Some hardline generals insisted this was propaganda, that Hiroshima had been destroyed conventionally, and the Americans were lying about a superweapon. Others weren't sure. They urgently turned to their scientists for answers. Nishina was immediately summoned to the military command center. As he traveled through the bombed-out streets of Tokyo, his mind raced, rerunning calculations. The energy release described suggested a yield of at least 15 kilotons of TNT equivalent, an almost perfect match for theoretical predictions he himself had made for a uranium-235 fission bomb. But the uranium required the enrichment process. It should have been utterly impossible to accomplish during wartime. At the command center, grim-faced officers bombarded him with urgent questions. Dr. Nishina, was this truly an atomic bomb? Could the Americans actually have built such a weapon? How many more do they possess? Nishina, trained as a meticulous scientist, gave them an answer they didn't want to hear. Based on the descriptions provided, yes, this appears to be an atomic explosion. He elaborated. The intensity of the flash, the unprecedented thermal radiation, the vast blast radius, and the characteristic formation of the mushroom cloud all matched our theoretical predictions with horrifying precision. But then, in what would prove to be his second catastrophic miscalculation, Nishina offered a small glimmer of false hope. He reasoned that if the Americans had successfully built one atomic bomb, it must have consumed their entire supply of enriched uranium. Building a second bomb, he asserted, would likely take months, possibly even years. Japan, he concluded, might still have a window of time to negotiate surrender terms. He was wrong again. The Americans already had a second bomb ready. Fat Man, a plutonium implosion device, was being prepared on Tinian Island at that very moment. By August 7th, Nishina's initial investigation team, which included Dr. Saburo Asaida, a respected meteorologist and physicist from the Riken Institute, had managed to reach the desolate ruins of Hiroshima. What they found defied human comprehension. Dr. Asaida walked through the grotesque landscape, his Geiger counter clicking frantically. The radiation readings were unmistakably high, confirming induced radioactivity. The sheer scale of the destruction, however, went far beyond their most pessimistic theoretical predictions. Their models hadn't fully accounted for the terrifying efficiency of the thermal radiation effects. The instantaneous incineration, the horrific firestorms, and the insidious, delayed killer, radiation poisoning. Asaida meticulously collected samples of fused sand and metal from what had been ground zero. Under the extreme temperatures of an atomic blast, ordinary silicate sand melts and vitrifies into glass. He found greenish, bubbly glass everywhere near the hypocenter. He later calculated the temperature required, well over 3,000 degrees Celsius, 5,400 degrees Fahrenheit. This physical evidence unequivocally confirmed atomic fission. The most damning scientific evidence came from spectroscopic analysis. By examining the residual radioactive isotopes in the debris, Asaida and his team could determine the specific type of bomb used. The characteristic signatures pointed to uranium-235. The Americans had indeed solved the enrichment problem, and not just theoretically, but industrially. When Asaida's detailed report reached Tokyo on the evening of August 8th, Dr. Nishina absorbed its contents with a profound, gut-wrenching realization. He finally understood the true, terrifying magnitude of their collective miscalculation. The Americans hadn't just built one bomb through some stroke of luck. They had industrialized the entire process of nuclear weapons production. The 64 kilograms of highly enriched uranium-235 required for Little Boy represented a level of industrial capacity that Nishina's entire NIGO team couldn't have matched in decades. He sat in his laboratory that evening, surrounded by his small thermal diffusion columns, and did the mathematics. If the Americans had enriched 64 kilograms of uranium-235 to 80% purity in approximately 2 years, based on intelligence estimates of when the Manhattan Project had begun serious enrichment work, then they must have constructed separation facilities at least 1,000 times larger than Japan's entire atomic program. 1,000 times! The number was astronomical. It meant that while Nishina had been painstakingly scraping together equipment, the Americans had been constructing entire industrial complexes on a scale that Japan, with its war-depleted economy, couldn't even begin to match. But worse was the chilling implication about future bombs. If the Americans possessed this much capacity, they didn't just have one bomb. They had more. They could be producing them regularly. Nishina calculated potential production rates. Another bomb every few weeks or months. Japan had absolutely no defense. No air defense system could stop a single B-29 carrying a single bomb. No amount of fighting spirit could withstand weapons that could vaporize entire cities in seconds. On the evening of August 8th, Dr. Nishina prepared his final report for the Imperial High Command. He wrote with the precision of a scientist, but the urgency of a man who fully understood the existential catastrophe. The Americans, he articulated, had demonstrated capabilities far beyond Japanese estimates. They possessed not just one atomic bomb, but potentially an arsenal. Continued resistance was mathematically and practically futile. Nishina's grim report reached the Supreme Council for the direction of the war, the Big Six, on the morning of August 9th. They were already meeting, reeling from the Soviet Union's surprise declaration of war, which had come just after midnight, followed by a massive invasion of Japanese-held Manchuria. The strategic situation was collapsing from multiple directions. At 11:02 a.m. on August 9, 1945, as the Supreme Council debated, Fat Man detonated above Nagasaki. This time, Nishina didn't need investigation teams. The news of a second bomb, just 3 days after Hiroshima, chillingly confirmed his worst calculation. The Americans indeed had production capacity. They could, and clearly would, destroy Japanese cities one by one until nothing remained. But something even more devastating, more profoundly shattering, in the Nagasaki bombing affected Nishina personally. Fat Man was not a uranium bomb. It was a plutonium implosion device. This revealed a chilling truth. The Americans had not just pursued a single path to fission weapons. They had pursued multiple, entirely different paths simultaneously. While Japan's single struggling research program had focused all its limited resources on uranium enrichment, the Americans had built not only vast uranium enrichment facilities, but also massive plutonium production reactors. They had effectively hedged their bets with overwhelming redundancy of industrial resources. Nishina's team obtained spectroscopic analysis of the Nagasaki debris within days, confirming plutonium-239. This meant the Americans had operating nuclear reactors capable of transmuted uranium-238 into plutonium. The massive reactors at Hanford represented yet another industrial undertaking that Nishina hadn't believed possible during wartime. The depth of their ignorance regarding the Manhattan Project's scale was unfathomable. The true, staggering scale of the Manhattan Project only became clearer over the following weeks and months as Japan surrendered unconditionally on August 15th and the Allied occupation began. Nishina, now in direct contact with American scientists, began to learn the astonishing facts. The Americans had spent an astounding $2 billion on the project during the war, an astronomical sum in 1945, equivalent to nearly $30 billion in modern currency. They had employed an astounding 130,000 workers across multiple, vast, top-secret sites. They had involved dozens of Nobel Prize winners and hundreds of the world's top physicists, chemists, and engineers. Japan's entire NIGO program, by stark contrast, had employed fewer than 100 people. Its total budget wouldn't have paid for 1 month of Manhattan Project operations. The disparity was galactic. The Americans, Nishina realized, had not approached the atomic bomb primarily as a pure scientific challenge. Instead, they had treated it as an immense engineering problem, a colossal industrial puzzle to be solved through the application of absolutely massive, seemingly unlimited resources, unbridled pragmatism, and sheer industrial brute force. They had built redundant systems, relentlessly pursued parallel research paths, and thrown staggering sums of money at every conceivable obstacle. When one uranium enrichment method proved too slow, they simultaneously built facilities for multiple other methods. When critical materials like copper became scarce, they simply borrowed 14,700 tons of silver from the U.S. Treasury. When they needed more scientists, they recruited relentlessly. Japan, by contrast, had approached the atomic bomb exclusively as a pure science problem, assuming that theoretical knowledge and careful laboratory research would be sufficient. Nishina had assumed that physics alone determined what was possible, not fully recognizing that American industrial capacity could simply overwhelm theoretical difficulties, brute forcing solutions to problems that seemed practically impossible. There was a profound irony in this realization. Nishina had studied under Niels Bohr, one of the founders of nuclear physics. He understood atomic theory as well as Robert Oppenheimer or Enrico Fermi. Japanese scientists had made genuine contributions to nuclear physics in the 1930s. Hideki Yukawa would win the Nobel Prize in 1949 for his work on mesons. The knowledge gap had not been the problem. The industrial gap had been utterly insurmountable. After the surrender, Nishina met with prominent American scientists who arrived as part of the occupation forces. They toured his laboratory at the Riken Institute, examining his small thermal diffusion columns and his pre-war cyclotron. The Americans were respectful, but Nishina perceived the underlying pity in their eyes. His entire program was smaller than a single building at the vast Oak Ridge complex. One American scientist, attempting to be kind, remarked that Nishina's thermal diffusion approach was theoretically sound. Indeed, the Americans had actually used thermal diffusion as one of their enrichment methods. Nishina's science had been correct. He simply hadn't possessed the resources or the industrial might to scale it up. But this was cold comfort. In the brutal calculus of total war, correct scientific theory without massive industrial capacity meant nothing. The Americans hadn't won the race to the atomic bomb through superior physics. They had won through superior industrial organization, seemingly unlimited resources, and a pragmatic willingness to pursue any approach that might work. Dr. Yoshio Nishina spent his remaining years reflecting on this profound miscalculation. He had assumed that American scientists would face the same severe limitations he had faced. He had projected his own resource limitations onto his adversaries, assuming that physics itself created insurmountable practical barriers for everyone. He hadn't understood that America's colossal industrial economy, even while fighting a two-ocean war, possessed spare capacity that exceeded Japan's entire pre-war industrial base. The Americans could build secret cities, employ 75,000 workers on a single facility, and spend billions on a weapon that might not work, all while simultaneously producing thousands of ships, tens of thousands of aircraft, and millions of tons of conventional munitions. The atomic bomb had been a scientific achievement, yes, but more fundamentally, it had been an unparalleled demonstration of industrial capacity, so overwhelming that it could not be matched by any other nation on Earth in 1945. Japanese scientists, including the brilliant Dr. Nishina, had fatally underestimated this capacity until the moment Hiroshima disappeared. By then, the tragic miscalculation had cost hundreds of thousands of lives and had irrevocably ensured Japan's unconditional surrender. In his final writings, Nishina acknowledged the error. He had correctly calculated what was theoretically difficult and, from his constrained perspective, assumed it was practically impossible. He had failed to imagine that America would simply overwhelm theoretical difficulties with sheer, unrelenting industrial force. That profound failure of imagination, more than any gap in scientific knowledge, had defined Japan's atomic program and its inevitable failure. On August 6, 1945, at 8:15 a.m., Dr. Yoshio Nishina learned a brutal, indelible lesson. In modern total warfare, industrial capacity, organizational prowess, and the raw application of resources often matter more than theoretical knowledge. The Americans hadn't outsmarted Japan's scientists. They had simply outbuilt them by a factor so large that direct comparison became meaningless. And in that devastating realization lay perhaps the most important lesson of the dawn of the atomic age. In the relentless global race for ultimate weapons, overwhelming resources and meticulous organization will triumph over scientific elegance and theoretical sophistication every single time